Sir Isaac Newton formulated three fundamental laws that form the foundation of classical mechanics. Let's start with Newton's first law, also known as the law of inertia. According to the first law, an object at rest will stay at rest unless acted upon by an unbalanced force. When a force is applied to the book, it begins to move. Similarly, an object in motion will stay in motion with the same speed and in the same direction unless acted upon by an external force. In an ideal environment with no friction, a ball set in motion would continue moving forever at constant velocity. But in reality, friction acts as an external force that slows the ball down until it eventually stops. Now, let's explore Newton's second law of motion. The second law states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. Let's compare how the same force affects objects of different masses. When we apply the same force to both objects, the object with less mass accelerates more than the object with greater mass. Now, let's see what happens when we apply different forces to objects of the same mass. The object with the larger force applied to it will accelerate more than the object with the smaller force, even though they have the same mass. To summarize Newton's second law, the acceleration of an object is directly proportional to the force applied and inversely proportional to its mass. Newton's third law states that for every action, there is an equal and opposite reaction. Mathematically, when object A exerts a force on object B simultaneously exerts a force equal in magnitude but opposite in direction on object A. Forces always come in pairs. When one object pushes or pulls on another, the second object simultaneously pushes or pulls on the first with equal strength, but in the opposite direction. Let's explore some real-world examples of Newton's third law in action. Rocket propulsion is a perfect example of Newton's third law. As the rocket expels exhaust gases backward, the gases exert an equal and opposite force that propels the rocket forward. This is how rockets can accelerate in the vacuum of space, where there's nothing to push against except the exhaust itself. When we walk, we push backward against the ground with our feet. According to Newton's third law, the ground simultaneously pushes us forward with an equal force, allowing us to move. This action-reaction pair is what enables us to walk, run, and move around on any surface. Now, let's see how all three of Newton's laws work together in everyday scenarios. When driving a car, all three laws come into play. According to the first law, a parked car remains stationary until a force acts on it. The second law explains that when the engine applies a force, the car accelerates proportionally to that force, and inversely to the car's mass. And the third law shows that as the car's wheels push backward against the road pushes the car forward with equal force. These three principles working together explain how cars and other vehicles accelerate, maintain constant speed, and brake. Newton's three laws of motion have formed the foundation of classical physics for over 300 years. These elegant principles explain nearly all macroscopic motion in our universe, from everyday activities to complex engineering and space exploration. Together, these three laws provide a comprehensive framework for understanding and predicting how objects move and interact in the physical world.